Okay, 1, 2, 3 is like quarter to 4 in the morning. Let us start. Um, I'll start from here. Should I? What was previously? Um, should I read? Should I reread this? Solution of homogeneous. Uh, I don't think I'll reread that. Maybe the last sentence. We have obtained the R by R matrix R containing R linearly independent column vectors. The determinant does not vanish, hence R is a non-singular invertible matrix. The order R of submatrix R is called the rank of the matrix A or B. So like rank is how much independent um, row vectors that are in the determinant, not necessarily how much rows the determinant has. So 7 by 7 that has 4 independent row vectors has a rank of 4. That's how I read this. That's how that reads to me. Um, okay. Experimental fact linear momentum in massive object P equal mv is always parallel to its linear velocity. The angular momentum L of a rigid body is not always parallel to its angular velocity. The classic illustration of the observation is a rotating dumbbell made of 2 point masses connected by massless rigid rod of 2r. Is rotated about the midpoint O about the z-axis with angular speed omega. Angular momentum L equal r cross p is always perpendicular to the dumbbell axis if theta is not equal to 0. Consequently, it is not always parallel to omega. The angular momentum is always perpendicular to the dumbbell axis, r cross p. So p is linear momentum, right? Linear momentum p. R is in this direction. P is, I assume it's in the v direction, which is this, yeah. So R cross P would be in the um perpendicular to the plane, which is um parallel to the axis of rotation. Yeah, yeah. Um, it's always perpendicular to the dumbbell axis if theta is not equal to 0. So if theta is 0, R is this, and hmm, I guess MV. I guess the point is if theta is 0, then the velocity vector doesn't exist, question mark, which means that um, L can be in the axis, L can be in EZ, or it can be in EY. It can span that entire plane. Like earlier, we were seeing homogeneous equations. Um, okay, is that what they're saying though? The angular momentum L across R cross B is always perpendicular to the dumbbell axis if theta not equal to 0. Consequently, it is not always parallel to omega. So omega okay, here, like down here, they're saying omega, wait, mr cross v. V equal omega cross r. V equal omega cross r. Velocity. So these three guys are perpendicular, right? So these three guys are perpendicular. So r, v, and omega is always in the z-axis. Yeah? Yeah. Um, Consequently, it is not always parallel to omega. So when theta is 0, um, is it doesn't have to be parallel. It can be in the y plane. Not, not the y plane. Yeah? It can bleed into the y-axis, the zy plane. Um, however, both L and omega are 3D column vectors when expressed in matrix notation. Blung, blung, blung. 3D column vectors when expressed in matrix notation. Hence, there exists a tree square matrix I that can connect them. L and omega are 3D column vectors. L equal R cross P. R cross P. R cross P. Boom, 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 boom. L equal R cross P. How would you write this? You would write this as determinant of R of I, well, Rx, Ry, Rc, Px, Py, Pz, and boom, you have a tree by tree. And you can do the same for the omega. Omega is a tree by tree. Does that make sense? So since both of these are tree by trees, um, hmm, like in like last session I was like, oh, um, I was like, hence there exists a Chirurgy matrix. Why? And I was like, if we have two matrices A and B, is there always an M such that you can connect them like AM equal B? And it was like, if you did that, you would arrive at this equation. M would have to be the inverse of something, one of them. Matrix multiplication would be, but to get the inverse of something, it needs to be a square matrix. So I was confused because column vector says that, oh, it's a 1 by 3 or something, right? A 3 by 1. The 3D column vectors. But now I've done the logic shenanigans to make it a 3 by 3. I could be wrong, but let's just roll with it. So L equal I omega, or Li, the I component of L equal, um, the I component of L equal, I think this is just matrix multiplication definition. I should really write down the matrix multiplication definition. Where are you, son? Um, Where am I? Ah, it's up here. C I J equals summation of ah K equal 1 to N A I K B K J um yeah, okay. Um is this matrix multiplication? The I component, we're ignoring J because hmm, okay, earlier I said this was technically a 3 by 3, but we're once again treating it as a 3 by 1. Um, hmm, hmm. It is a 3 by 1 because when you compute this determinant, you get I plus J plus K. Uh, Li equal, what do we call row I, column J? Let's call IJ where J is 1, right? J is 1. And hmm, hmm, Li, Li, well, let me draw it. Well, not really draw, but boom equal this true right true guy times this. Okay, we want to find the second guy here. So we do this multiplied by this. This is row 2, and you just sum up all the columns, right? So I2, all the columns. And this is sum up all the columns. So we go into all the J's. Omega 1, omega 2, omega 3, omega 4. 1, 2, 3, 4. I is hmm. Well, I being 1 doesn't make any sense, right? I L I J omega J. Let's continue. I is called the initial matrix for a special case of point mass. We have what the base 0. So point mass, um, angular momentum equal mr cross v, which is this. If you substitute the term for velocity, and from BSC rule we get this, right? Um, this is BSC rule over here. A cross B cross C. So B would be uh um you get B A dot C minus C A dot B. This R dot R will be R squared, and this R dot omega would be R dot omega would be Rx omega x plus ry omega y plus rz omega z. Um, r squared l l um. There's a 3 by 1. There's a 3 by 1. 3 by 1. 3 by 1. 3 by 3. 3 by 1. 3 3 3 1. 3 by 3. L. To get from L to I, we need to divide by omega. Is there another way to do that? Or not divide by omega? Hmm. L divided by omega. What does it mean to divide two vectors? What does it mean to divide a vector by another vector? What does it mean to multiply a vector by another vector? Well, there are multiple ways to do it, right? Scalar product, vector product, tensor product. Um, hmm, hmm. R dot. Let's just roll with what they're saying for now. Okay. In vector notation, to write the relation matrix notation, we know that Li, we have to work from here again. Li equal m r squared omega I. Okay, Ci equal ai plus vi, right? So you just ignore the j's and k's. So yeah, I can work with this so far. Minus r dot omega. R dot omega. Li. So xi, yeah. And so at the end of the day, r dot omega is just a constant, right? So this, so if this is 3 minus r3, that's minus 3i minus 3j minus 3k. So this is the only guy that really matters. And this is just a number. So we're going through all, we need to find a number to see how much this xi is affected. So I agree with this so far. And that's the entire thing. Yeah. Mr squared. Okay, now we're factoring out omega j. Are we allowed to do that? Like from here, I mean. I really like my bracket. Is this a bracket? I really like my brackets. Okay, well, let me. R squared. Okay, if you're factoring something out of something out of something, you're like dividing, right? So what they're saying is r squared omega I divided by omega j is r squared Kronecker delta ij. That's what they're saying. Omega j. Or they're saying that you can factor out the r squared, right? Um, Alternatively, they're saying omega j multiplied by Crank delta ij equal omega I. Um, if I is equal to j, then this is 1, and this is omega I equal omega I would make sense. If I is not equal to j, this is 0. Uh, this is 0. If I is not equal to j, omega j is 0 equal omega I. This entire term becomes 0. Does that not matter? R squared omega I. Carbon delta ij 0. If I equal j, this is 1. Yeah, that makes sense because wi over wi, that's just 1, right? If they're not the same, this is 0. This division is 0. What does that mean? That means wi is 0. 0 divided by something is 0. wi. If I is not equal to j, if I is not equal to j, what does that mean? What is j? Okay, I is the I component, the x component, the ex component of li. So that's the first term in the column vector. J goes from 1 to, like, let's assume we're doing with treaty. J goes from 1 to 3. J goes from 1 to 3. Wait. There's a big difference here. This summation, they move the summation from this one thing to the entire thing. So we're summing the entire thing over J. That changes a lot, actually. Okay, so I don't think anything changes here, but does it? Xi, Xj. I don't think anything changes here, really. But over here, okay, m r squared omega ij equal m r squared omega I. Okay, I see it. So originally, over here, there's only the I term. There's only omega I. There's no other shenanigans. So a way to get rid of everything except I is to introduce Kranka delta ij, because omega is j, right? So anytime I is not equal to j, we get 0. We're fine with the zero because there weren't any other terms here anyways. We only had the omega I term. We don't care about the others. So yeah, I agree with this. I agree with this. Um, xi summation j x j omega j. They're saying this is equal to xi x j omega j. Is this summation just for this bracket or is it for the entire thing? Does that matter? I think it's for the entire thing. Yeah. Omega j. Okay, let's move. Mr squared. And the reason they put the summation outside is so they can factor out this omega guy. So they can make the conversion of L to I easy with just the division of omega I. Li to initial matrix Ij is just divided by omega I. Okay. Having established L in general, not parallel. Having established that L is in general not parallel to omega. How did we establish that? Oh, omega cross R. Omega cross R lies in the plane perpendicular to omega and R. Now you cross that with R, you get, okay, omega cross R. We have this direction here. This cross R, we have this. Back to omega. Yeah. Well, the direction is back to omega. It doesn't, the magnitude is different, surely. Hmm. Omega minus R. So from here we see that L is equal to a multiple of omega. So right now we're in, let's call this the y-axis, I don't know, the z. We're in the axis with omega, right? So L equal a multiple of omega minus a multiple of R. Bling, bling. Omega R. L is in general not parallel to omega. For omega to be parallel to L, R dot W needs to be 0, right? Yeah. R dot omega needs to be 0 for omega being parallel to L. We may ask next if occasionally they might be. It's easy to see that for the rotating dumbbell, there are in the three directions along which it occurs. Of these omegas is parallel to the dumbbell axis. Theta equals 0. If theta equals 0, okay, I've been thinking of this like Rx omega x plus Ry omega y plus Rz omega z. But I forgot that cross dot product could be R omega cos theta, where theta is the cos theta Rw, angle between R and W. If theta is 0, that means what if omega is up here? It's not another 90 degrees. Cos 90 is 0. Cos 90 is 0. But doesn't that mean that it's a 0 always? 0. When is theta not 90? When is theta not 90? R omega. When is omega not perpendicular to R? R cross, it is always perpendicular to R. X. While the remaining two, one of these omegas is parallel to the double axis, while the remaining two are perpendicular to the what? One of these omegas is parallel to the double axis. Theta equals 0. While the remaining two perpendicular to the, or parallel and perpendicular. It's parallel, perpendicular. These are actually called the principal axes of inertia. The corresponding inertial parameters L and omega are called. The existence of three principal axes of inertia turns out to be a universal property of rigid bodies. The parallelism between L and omega expressed by this. L equal I omega, right? L equal I omega. I omega equal this mess. I omega equal mr squared omega minus r dot omega. They're parallel if this term is 0. Okay, the parallelism between L and omega along these special directions is expressed by the condition this. Yeah, where lambda is mr squared. Where the scale proportionally constant, this is called an eigenvalue or characteristic value of the initial matrix. Lambda is called the eigenvalue or characteristic value of this. Equation 2.48 is called the eigenvalue equation and eigenvalue equation. Interesting mathematical observation that this equation can be solved for the special directions omega. This equation can be solved for the special directions omega for the eigenvalue and for the eigenvalue associated with each of these directions. We'll see what they mean. We'll see what they mean. Now we're actually on to new stuff. I'll drink water. Solution of the eigenvalue problem. So we're trying to solve this. We shall write the general matrix eigenvalue equation. General matrix eigenvalue equation as a homogeneous equation. We have declared matrix B should be square, otherwise BU will not have the same dimension as U. BU as U and cannot possibly satisfy the equation. I agree that should be square, yeah. It also follows from the results from the last section that non-trivial solutions with U not equal to 0 can only appear if the determinant vanishes. Determinant vanishes. Okay, let's just go back up for a little refresher. Yeah. Okay, the determinant is 0. The determinant vanishes if two guys are the same, right? If two guys are parallel, the determinant vanishes, which means the solution can span more than, depending on the dimension, how much dimensions we're dealing with. The amount of, for each parallel, for each dependent row vector, there's an additional dimension for the solution to exist in. Okay. It follows from the result that non-trivial solutions with U not being 0 can appear only if the determinant vanishes. Phi of lambda is called a characteristic of secular determinant. If matrix B is n times n, phi of lambda is a polynomial of degree n in lambda. Okay, phi of lambda is just a determinant of b minus lambda I, which is okay. Lambda is not present. Lambda is only present in the diagonals because I is only 1 in the diagonals and 0 elsewhere. So phi of lambda is just B. It's just B matrix with minus lambda in the diagonals. If matrix B is n times n, phi of lambda, phi, I should say phi because it's phi. Phi lambda is a polynomial of degree n lambda. Polynomial of degree n lambda. Yeah. Because if we find the determinant of this, we need to multiply this by this determinant here, which is this multiplied by this determinant here. And each time you keep getting another lambda. So 1, 2, 3, 4. You get a lambda to the nth degree, lambda n. Lambda bling bling. Do you also get a lambda n minus 1? Lambda 1 lambda times lambda lambda minus nothing. Lambda 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 blah, 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 blah. Maybe you only get this. Maybe it's like lambda to the 3 plus lambda to the 5. I don't know. If I compute it, I can figure it out. But let's just keep going. If matrix B is untimes n, phi of lambda is a polynomial of degree n, and lambda, the determinantal condition phi lambda equals 0. Call the characteristic equation. Did they not already use that? Eigenvalue, characteristic value. I guess not. Characteristic determinant. Characteristic equation. Characteristic value. Okay, let me write this on the side. Lambda characteristic value. Phi of lambda characteristic determinant. Making phi of lambda equals 0 is characteristic equation. Yeah. Secular. Eigenvalue. Okay, call the characteristic a secular equation. Therefore has n roots. So yeah, there is. Wait, no. Therefore has n roots, yeah, which are not necessarily different. When lambda equal lambda I. So when we substitute back into the equation or back into the determinant, if we substitute one of the roots of lambda into the determinant for lambda, the determinant vanishes. Equation 2.49, this can then be non-trivial solution. Okay, so since this is 0, this could be anything. Yeah. Thus the n roots are the only possible eigenvalues. Thus the n roots are the only possible eigenvalues. when the matrix B is n by n. Yeah, I guess. To illustrate the calculation of eigenvalues, let's consider 2 by 2 matrix. Okay, phi of V would be determinant B, so A minus lambda I, B minus lambda I equal, okay, A minus lambda I, well, just lambda, right? Minus lambda. A minus lambda multiply B minus lambda, B minus lambda. You had A by B, AB plus lambda squared minus lambda B um, minus lambda A. This minus CD. Okay. Lambda minus the sum of A and B. Lambda plus AB minus CD equals 0. It has roots. So we're solving for lambda. We just use quadratic formula equation. I don't know. Minus b plus or minus the square root of b squared minus ac minus b. I feel like I'm missing something. Over 2 something. Yeah, over 2a. Anyway, yeah, I think it's over 2a. A is 1, a equal 1, b equal a plus b. Let me use capital A, capital B, and capital C equal AB minus CD. Minus B would be, oh, well, this is minus B, right? Minus B would be minus minus a plus b. So a plus b minus b plus or minus square root b squared minus 4ac. B squared is minus a plus b squared. Minus 4ac. A is 1. C is ab minus cd. Over 2a. A is 1. So 2, 1. We should, let's just compare these now. This half is just this 2. Um, half a plus b, yeah. Plus or minus, yeah. Square root minus a. Okay, so we have the 4D. Wait. Minus 4ac. 4ac. What's c? ab minus cd. Okay, I could have written this better. This is so scrappy. Minus 4ac. A is 1. C is ab minus cd. So minus 4 minus cd, we get 4cd. Minus 4 times ab minus 4ab. Yeah. A minus b squared is what? A squared minus b squared minus 2ab. Yeah, minus 2ab. Question mark. Minus a plus b squared minus a minus b squared equal a squared plus b squared Uh, minus 2. Why can't I do this? Minus a minus b. Minus a minus b. Minus a times minus b is ab. 2ab. Positive 2ab. So, and if we add that to the 4ab we had here, a squared minus b squared. Okay, something is fishy, but I'm just gonna blame. I'm just gonna blame myself. I did something wrong, but I trust. I trust that if I did it correct, I'll end up with this. Okay. That satisfied the usual identity. Has two roots. The two roots is this: half a plus b plus or minus this. It satisfies the usual identity lambda 1 plus lambda 2 equal a plus b equal trace of b. Trace of b is this. Okay, what does the trace of b look like? Trace of b is lambda minus lambda multiplied by n plus minus lambda multiplied by n. No. Trace of b, not trace of this entire thing. What is b? The result turns out to be a special case of the general theorem that states this is a special case of the theorem that states that the sum of eigenvalues of a matrix of any order is equal to its trace. Sum of the eigenvalues of a matrix is equal to its trace. The proof is left as an exercise. An eigenvalue. A plus b plus or minus. Okay. So lambda 1 is half a plus b plus this. Lambda 2 is half of a plus b minus this. So the plus and minuses cancel out. The two halves combine to get a plus b. How is a plus b trace of b now? A plus b is trace of b. What is a plus b? A plus b. Oh well. Well, that's just this, right? That's just for 2 by 2. Okay. Well, let's roll with it. I think I've proved it enough to myself. The sum of the eigenvalues equal the trace. Okay. As we were discussing in the last section, only the directions of the non-trivial solutions are determined, not their lengths. The eigenvalue equation may be written more precisely as. So originally, phi equal b, phi equal determinant b minus lambda I. V equals 0. Determinant equals 0. The eigenvalue equation may be written more precisely as this. So originally we have determinant b minus lambda I equals 0. So the 0 doesn't change. Uh, uh, lambda I b minus lambda I ei. Are we no longer dealing with determinants? Because this should be a number, but this is a direction. B, BEI equal lambda IEI. Only the directions of non-trivial solutions are determined, not their lengths. Matrix eigenvalue. Matrix eigenvalue equation. Characteristic equation. Okay, so it is not the same thing. Characteristic equation is not the matrix eigenvalue equation. To express where. Okay, this is the eigenvalue equation. I omega equal lambda omega. Yeah, I omega equal lambda omega. Yeah, maybe. B minus lambda I equals 0. I lambda I omega. Okay, I'll come back to this later. Thus, the matrix eigenvalue equation may be written as this, where B minus lambda I EI equals 0. B minus 1 EI. So the I component of B minus, what is the I component? B is a matrix. What is the I component of a matrix? Does that even make sense? I J K L B minus lambda I or B EI equal lambda EI. BI equal lambda. We call EI the eigenvector belonging to the eigenvalue. We call EI the eigenvector belonging to the eigenvalue lambda I. Since we already know how to solve homogeneous matrix equation, the eigenvalue equation, we keep getting new equations. Can we solve to obtain EI? Procedures illustrated in for examples. We keep getting new equations. Oh my god. This is the eigenvalue equation. I omega lambda omega. eigenvalue equation. Yeah, yeah. It's called an eigenvalue equation. We shall write a general matrix eigenvalue equation is this. Bu equal. Okay, so this generalized, where we factor the omega, bring it to one side. Okay. Yeah. So I omega minus lambda omega, factor out omega. I is initial matrix minus lambda. And I guess we slap on the identity matrix to lambda to be like, oh, this is a matrix, by the way. Maybe, yeah. Okay. I guess I should erase this then. So these two are technically the same. B minus I lambda U equals 0. Ah. General eigenvalue equation. B should be square. Bu will not have the same dimension as U. Results last section. U non-trivial solution with U not equal to 0 can appear only a pair of determinant vanishes. Yeah. Characteristic determinant. Matrix B is M by N. Polynomial of degree N in lambda. Therefore, N has roots which are not necessarily different. When lambda equal lambda I, determinant vanishes. Yeah, that's just how roots are. This can then have a non-trivial solution UI. Thus, the N roots are the only possible eigenvalues. To illustrate the calculation of eigenvalues. Okay. Proof of this general term. The directions of the non-trivial solutions are determined. Thus, the matrix eigenvalue equations may be written more precisely as. Okay, so we're getting even more general. B minus lambda I equal EI. EI equals 0. BEI. Okay, so it's misleading to be like, oh, we're finding for UI because we're never going to find out the length, because that's how homogeneous equations work with. That's just how it works. So To make it less misleading, we want it to be like EI. We're only promising to find the direction when we find the solution. So that's what we're doing here. EI lambda I. EI lambda I. Determinant 0. Determinant is 0. For the determinant to be 0, two guys need to be parallel. Two guys need to be parallel. BEI. Okay. So I know how to solve homogeneous equation. The eigenvalue equation can be solved to get EI. Okay, a uniform solid sphere has an inertial matrix of this. Characteristic equation phi of lambda equal phi of lambda is determinant of this equals 0. Determinant of this is, oh my god, b minus lambda I. 1 minus lambda, 1 minus lambda, 1 minus lambda. The determinant of this is for real 1 minus lambda to the power 3. How do you find the roots of this? Well, we already factorized everything, right? Yeah, this is already factorized. Like normally we would factorize it and then be like, oh, the other side is 0. So we'll just divide out the other factors. So we'll just get 1 minus lambda equals 0. Lambda equal 1. So that the true roots, identical eigenvalues like these, are said to be degenerate. Degenerate. The eigenvectors are calculated from homogeneous equation. This where A equal the eigenvectors for an homogeneous equation. Since we already know the self-homogeneous matrix equation, the eigenvalue equation, the EI. So we're treating this as A, and this as X, and this as C. A is B minus, yeah, so this is, okay, yeah. This shows that omega can be any, okay, let's not jump to that. That's just an interpretation of this. The eigenvectors are to be calculated. B characteristic equation minus lambda eigenvectors. How long have I been streaming? Hour and 10 minutes. Okay. This result tells us that omega can be any vector in space since there are three linearly independent. Okay, yeah, they're saying since these three are identical, these three are parallel. Since there are three linearly independent vectors in space. I'm going to choose omega 1 equal EX, omega 2 equal EY, omega 3 equal EC. Obtain the eigenvalues and eigenvectors of this guy. What do we do first? First I want to do minus lambda. Then I want to find the determinant of this. We already did this earlier. This, that is, the one is below, a lambda 1 is under this. Lambda 2 is above this. Lambda 1 is below the mean of the diagonal matrix elements. Half A plus B. 2A. Okay, so depending on the rank, this bottom number, A plus B on 2. Okay. The lambda times lambda times lambda. Lambda times lambda times lambda. The coefficient of the lambdas is either 1 or minus 1, right? Because minus lambda times minus lambda, oh, the coefficient is 1. Add another times minus lambda, coefficient is minus 1, right? Yeah. 2A. Yeah. That is, lambda 1 is below the mean of the diagonal matrix elements by an amount. This. B minus A squared plus, oh, CC, so it's slightly different from what we did last time. Not CD. P squared minus 4AC. Okay. And below A itself. Okay. Oh my god. Lambda 1 is below this guy by this guy. So lambda 1 equal A plus B on 2 minus triangle minus delta. And below A itself by delta. Below A itself. Okay. Lambda 1 equal A minus something. A minus A by delta. They're saying this is the case. Delta is triangle plus half A minus B. Okay. Triangle plus half A minus half b. A, A, A. Minus half b. We get this. Minus triangle, we get this. Where does half a come from? Lambda 1 equal a plus b on 2. Oh, yeah. Um, this a is 1. This a is half. So 1 minus a half will remain back with a on 2. So yeah. Why are we doing this though? Well, omega 2 is above the mean by an amount. So omega 2 is a plus b over 2 plus triangle. Or it could also be omega lambda 2 equal b plus delta. Lambda 1 equal a minus delta. Well, why are we doing this? What is a delta is this guy. Okay. And deltas. Wait, both of them are deltas, I just realized. This is it okay to call it Chronica delta? I don't think so. Triangle is this, and delta is triangle plus half a minus b. Okay, delta is a little more complicated than this. Triangle, this, plus half a minus b, plus half a minus b, half a b minus. Okay, this is weird. But if I think hard enough, I'll make some equations about it. Any normalized 2D vector can be written in the form E equal cos theta sine theta. Any normalized 2D vector. What do you mean normalized? Does normalized mean you like turn it into a unit vector? I think so. Since cos squared theta plus sine squared theta equal 1 gives its normalization. Any normalized 2D vector. I guess let me Google that before I get lost. What is a normalized vector? Is a vector that's been scaled to have a length of 1, but still points in the same direction. Okay. Any normalized 2 vector can be written in the form this. Cos theta over cos theta sine theta. Cos theta I plus sine theta j. Sine theta j. So the I length, the I direction is cos theta. This is 1. This is 1. Cos equal adjacent and height. So we want to find adjacent. adjacent is h cos theta. H is 1, so A is cos theta. So yeah, this is cos theta, this is sin theta, yeah, correct. Since cos squared theta plus sin squared theta equal 1 gives its normalization, they're just saying, is this a nothing burger? The eigenvector EI satisfies the homogeneous equation. Yeah, that is... Wait, we're still dealing with this. Any normalized... Well, why are we getting into this? The eigenvector EI satisfies the homogeneous equation. This. S minus lambda I. Yeah, that is A minus lambda I. C multiplied by this equals 0. Okay, they just wanted a way to make this into like a column vector. Fair, I guess, fair. Do we actually find the values for lambda I? Oh, we can't. Well, these are letters, so it'll just be a general. Okay, tan theta I is sine and cos, which is... I guess we're just multiplying, right? Even if we're not, I'm gonna see what this results in. A minus lambda I cos theta I. Plus, okay, this... Wait, no, I'm doing this wrong. A minus lambda I... Wait, no, I was doing it correct. A minus lambda I cos theta I plus C sine theta I. That's just, yeah, equals 0 because this is equal to 0, 0, right? And also equal to 0 is this thing. C cos theta I plus B minus lambda I sine theta I tan theta I. We have these two equations. We have cos theta I, sin theta I, some product. No, not really a product, but some expression, C, C. Tan theta I equal lambda I minus A over C. How do we get this? Okay, let me let's keep the C guys on one side. Let's send over all the other guys on the other side. Is that a fair thing to do? We're gonna do it anyways. C sine theta I equal A minus lambda I cos theta I. C cos theta I equal... Well, this will be negative. Equal negative B minus lambda I sine theta I. This divided by this we'll give tan theta I equal, oh my god, well the negatives should cancel out, negative and negative. We have cosine sine. I don't want to do that. Um, we'll write it anyways. Cos and sine a minus lambda I, b minus lambda I. Wait, no, never mind. Sine a over okay, I think I see what they're getting at. So the first equation was 0 equal a minus lambda I cos theta I plus c sine theta I equals 0. Let's let's send this guy across. Sine theta c sine theta I equal a minus lambda I cos theta I, and also the negative because we're sending it across. I want to get rid of the c, so this becomes divided by c. I want to send this cos across to be like sine theta over cos theta. So this is removed from here. Sine theta over cos theta is tan theta. And on the other side we have over c a minus lambda I, but there's a negative here. So it's actually lambda I minus a. And we get this. And if we do the same thing for this, we'll get this. And from our earlier definitions, we were like lambda 1 equal a minus delta. So if we replace this with a minus delta, a minus a is 0. And then we just left delta. Lambda 1 equal a minus delta. So minus delta. And lambda 2 minus b. Lambda 2 minus b equal delta. You see, and they're also saying it's the negative cotangent of theta 1. Negative cotangent of theta. I'll unpack that soon. Cotangent of theta 1. Okay, I see what they mean. They're just relating these two equations. C, because C on delta, you just flip it. If you flip it and put a minus, you'll get this guy. So these two are related like that. If you flip and minus this, you'll end up here. Okay, I'm clicking everything, oh my god. Okay, hence, if theta equals theta 1, if theta, what is theta? If theta equals theta 1, tan theta 1, tan theta 2. Oh wait, tan theta 1, tan theta 2. Is theta 1 not the same as theta 2? I was under the impression that all of these was I. All of these is the same thing. Tan theta 1 is sine I, cos I. Let's just see where where they're going with this. If theta equal theta 1, then cos theta 2 equals minus sine theta. Okay, I am a little confused, clearly. If theta is theta 1, okay, let's just realize this relationship here. Tan theta 2 equal minus cotangent theta 1. What does this mean? This means sine theta 2 and cos theta 2 equal minus cos theta 1 and sine theta 1. If theta equal theta 1, cos theta and sine theta, then cos theta 2, this guy, equal minus sine theta 2 equal cos theta. So that is evaluating the correct word. They're equating the numerators and denominators of this relationship here. Are we allowed to do that? Are we allowed to do that? And what even is theta 1 and theta 2? Theta I, these two angles are the same. I understand, I understand. There's two eigenvalues. Yeah, eigenvectors. The two eigenvalues. We get a different theta for each eigenvalue. So yeah. So yeah. Okay, I understand. This shows that E2 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 is cos theta 2 sine theta 2. Cos theta 2 sine theta 2 minus sine cos. What about theta 1? Theta 1 would just be theta cos theta sine theta. I believe E1 should be cos theta sine theta, yeah. It's perpendicular to E1. How can I prove that these are perpendicular? Cross product should be E3. Does that even exist? Dot product should be dot product is contains the angle, right? So cos 90 should be 0. So your dot product of these should be 0. Sine theta times cos theta is minus sine cos theta. This times this is minus sine theta cos theta. This times this is positive cos theta sine theta. Add them up, you get 0. Okay, good. Blah blah blah, yep. I should end soon, if not right now. Let me see how far till the next break. Okay, we have a while till the next stopping point. So I'll stop for now. Yeah, even this next example is a while. So this is a good stopping point. Um, we did a good amount. We did a good amount. Farewell, the end of stream. Goodbye, goodbye, goodbye.